All right, so we're ready to talk about cardinality. That's sort of what we've been building to with our discussion of functions. Okay, functions are really great because they give us a way to talk about relationships between sets that's fairly efficient. When it comes to cardinality, we're going to be talking about relative sizes of sets. Okay, so let's say I have a surjective function from one set x to another set y. So this could look like the following. Right, maybe it's something like this. But the point is, if f is surjective here, or if there exists a surjective function from x to y, there have to be at least as many elements in x as in y. That's the only way we're going to be able to hit everything in y. Okay, so there must be at least as many elements in x as in y. And let's talk about injections now. Okay, so if I have a function going from x to y that's injective, what can we say about the relative sizes of these sets? So different x and y than I had previously. Right? So everything in x has to go to something different from every other element. Something like this. So in order for that to happen, y has to have at least as many elements as x in order for there to be enough places to go to. Right? If we want distinct elements to be mapped to distinct places in y, right, y has to have size that's at least as big as x. That's the rough idea of how functions can tell us about relative sizes of sets here. So there must be at least as many elements in y as in x. So if both of these things are true, if there's a surjection from one set to the other and an injection from one set to the other, right? If there's a bijection, then we should be looking at sets of essentially the same size. So this is where our definition of cardinality comes in. Okay, so we say two sets x and y have the same cardinality if there's a bijection from x to y. Okay, let's see. Other notes about cardinality. Oh, right. If a set is finite, the cardinality is the number of elements in the set. So if a set is finite, its cardinality is the number of elements it contains. Okay, so comparing cardinalities of sets is our precise way of comparing the sizes of sets. All right, so we only ever say that two sets have the same cardinality if there's a bijection between them, right? And the discussion before gives some rough idea of why that is. All right, let's move to a new page here. Give a couple examples. So all right, so let's take this set here. X is the first 5 letters of the English alphabet. So it has cardinality 5. Okay, and this set, Y, containing F, G, H, I, and J, has the same cardinality. Okay, there are certainly many bijections between these two sets. I mean, here's one: just send A to F, B to G, C to H, D to I, E to J. There's a bijection between the two sets. Okay. All right. Here's maybe a more interesting example with infinite sets. So 2z, the even integers, and z have the same cardinality. So you proved on the functions worksheet that there's a bijection between these. So here it is, the function from 2z to z, which is the halving function. So f of a equals half of a, is a bijection. Okay, so these two sets have the same cardinality, even though 2z is a proper subset of z, right? Z contains all the elements of 2z, and it contains extra ones as well, but in terms of cardinality, these are actually the same. So things can be a little strange when we're talking about infinity. Okay, so that's the thing to remember here, is that, I have one set that's a proper subset of the other, but because they're infinite, they can still have the same cardinality, right? And that's not true for finite sets, but it is possible for infinite sets. In fact, for any integer n, nz has the same cardinality as z, as long as n is not 0. So let me make a note of that. So actually, for any n in the integers, n not equal to 0, nz has the same cardinality as z. I'll leave this to you to think about how to prove. Right? I mean, it's certainly true for 2z, but maybe this will be a homework for you to think about. Okay, and then here's a definition related to cardinality that we're going to play around with quite a bit in our next video here. So we say a set is countable if its cardinality is the same as a subset of the natural numbers. Remember, the naturals are these numbers, 1, 2, 3, and so on. All are counting numbers. Okay, there are actually going to be two different types of countable sets. You can be finite, right? There are finite sets, finite subsets of n, or you can be countably infinite, right? If your cardinality is the same as the set of natural numbers n, then you would be countably infinite. So more on that in our next video.